Zach Stone here. You're about to watch part one of a 5-part series on power flow calculations that was put together by Gurus, our new continuing education program for professional engineers for licensure renewal. If you're not a professional licensed engineer just yet, if you're studying for the PE exam, then these videos are still going to be really helpful for you since power flow is a subject on the PE exam. In part number one of this video, we're going to work on deriving the formulas for complex receiving power. We're going to talk about the difference between terms such as buses, power transfer, and power flow. If you want to learn more about our new continuing education seminars for professional engineers, check out our continuing ed page at www.ohmgurus.com. Really excited to talk to you about power flow calculations and the transfer between two buses. I'm working on a new practice exam for the PE exam qualitative questions, and I came up with some really great questions on these for that new book. And I figured, hey, this would be a great topic to share with professional engineers as well. The reason why is a lot of other either books, white papers, other videos I've seen, I see discrepancies. I see people confusing the difference between power transferred and received by the receiving bus versus power transferred by the sending bus and power absorbed in the line. These are three different quantities. We're going to be talking about this today. So it's really important that we understand these three different quantities because depending on, if you're on the PE exam, they might ask for one of the three, or if you're dealing with a real life scenario, we got to make sure we're calculating the right amount for what we're expecting to get. So agenda today, quick speaker bio, that's me. We'll talk about the 3 learning objectives for the seminar. Brief description on just what the heck is power flow between buses, power flow or power transfer, same thing. After that, we're gonna do some math today. Don't feel like you got to memorize this. We're gonna go a little quick on it just because of time constraints, but we're gonna specifically derive the power transfer formula for complex power, for real power in watts, and for reactive power in VARs. The reason why we're going to do that is once we get to the end of those formulas, then we can look at those formulas and we can talk about all of the different power transfer relationships that we can infer from those formulas. Again, you don't have to have a strong math background. Just kind of sit back and I'll explain my steps while I work through it. It's just going to make a lot more intuitive sense of what it is that these quantities are that we're actually solving for. It's kind of like peeking under the hood, seeing how it all works. From there, I've got a wonderful case study for today. I'm used to a live class at night. We're going to be looking at the power transfer between 2 generators. We're going to be calculating all of the different power flow quantities and talking about the direction of each. And after that, I've got a really fun phasor diagram real-time system model. And I'm going to switch to it really quick. Can you guys tell me, can you see this on screen? Do you see the phasor diagrams on your screen? Yes, beautiful. So that's a wonderful tool. I spent a couple of weeks building it. I'm going to show you how all these variables interact in real time. After that, depending on how much time, we'll do an open Q&A. All right, so quick biography. You probably already know who I am. If you're here, I did see some newcomers. So really quick, I am a professionally licensed engineer in the Sunshine State of Florida. Of course, I have an ABET accredited Bachelor's of Science in Electrical Engineering degree. I passed both the FE and the PE exam on the first try. Most of my experience comes from the industrial world. Hard hat, steel-toed boots, high-vis, flame retardant clothing, fluke, wiggy in hand, 2 a.m. call-outs, design, maintenance, troubleshooting, you name it. That's where just about all of my experience comes from. I love math, right? Not most people do. I like it. To me, math is a bit of a puzzle. So I really like combining my love for math with electrical engineering. It just really helps to have a much better grasp on these real world concepts if we can explain the real world application with how these values interact. And of course, I love teaching others. I really enjoy sharing what I figured out on my own with you guys. I get a lot of enjoyment out of that. I've been primarily focused full-time running our PE class, helping engineers pass the PE exam since 2014, coming up on a decade here in October. 10 years. It's incredible. You can find me at our PE class website, electricalpereview.com. If you have any colleagues or friends that need to pass the FE exam first, you can find me at electricalfereview.com. This is a 100% free, forever, on-demand review course for the FE exam, so you can get started to licensure without having to spend a cent on a class. Omgurus.com, that's why you're all here today. This is our new continuing education program, also free. And probably my favorite is our online community for electrical engineers at powerpehelp.com. It's mostly focused on questions and answers for the PE exam, but in the future, we'll be hosting asynchronous discussions for continuing education like Omgurus. We do have a really engaged career and networking space, especially for the renewables industry. So if you're curious, pop over there, powerpehelp.com, and check it out. You can register for free and just talk to all of your peers. Yeah, it's the language of the universe, said John. All right, so today's learning objectives are threefold. Upon completing this professional development seminar, attendees, that's you, will be able to identify the factors that affect the amount of real power transfer between buses. And I see some of you already taken a stab at some of these quiz questions. You'll notice that's exactly what we're going to ask you on. Doing the same for identifying the factors, except this time that affect the amount of reactive power between buses. So P in watts, Q in vars. And then 3, calculate the amount of real and reactive power between two buses. We're going to do that today in our case study, and you got a question related to that in the quiz. All right, so what the heck is power flow between buses? So we've got two buses here on your screen. We've got a sending bus and a receiving bus. That's what those subscripts stand for, VS and VR. And we have a line reactance connecting the two buses. Most of you are familiar with the term bus, but where did that terminology come from? So bus, think of a really big, heavy-duty conductor, right? In the industry, especially if you worked on like motor control centers, you see the real big rectangular copper bus bars, real thick, handle a lot of current, hole punch through it so you can, lug some connectors on them. But a bus is a common electrical point where multiple circuits can be linked to distribute power. And I found this to be interesting. The term itself, bus, it comes from the Latin word omnibus, meaning for all, right? Big, connecting everything. So think of that. Bus, it's essentially a really large conductor where lots of other conductors connect to. Number 2, power flow between buses. So power flow, and specifically when we use the word power transfer, this is the amount that the receiving bus receives from the sending bus. So right here, this would be the amount of real power transferred to the receiving bus, received from one bus to another. This is equal to all of the power sent from the sending bus minus any power absorbed in the line. Now, typically when we work power flow or power transfer, we ignore line resistance. Anyone know why? For the most part, in high voltage systems, as the voltage gets bigger and the distance of that conductor gets larger, the reactance is much bigger than the line resistance. So what ends up happening is we essentially neglect the line resistance. We can assume the line resistance is approximately 0 because the reactance it's so much bigger that the effect the resistance has is negligible. So because of that, line resistance we usually ignore, which is why if you notice this conductor right here, all we have is a reactance symbol. We don't have a resistor symbol. Now, what are the applications of this? In the real world, all of this is done by what? All of this is done by system modeling. So everything we're going to teach today, how it's applicable to you, how it can help you is understanding exactly what that system model is doing under the hood. Really important, right? If we just assume that software is a magic box that is, it's never going to make any mistakes, it's infallible, well then we're likely setting ourselves up for failure. So it's really important to understand at least the basics of why it's doing what it should. How is this helpful to us? It can help us spot mistakes. It can help us know when something doesn't quite look like. It'll help us model systems better. And then the other benefit of this is in the real world too, it's an easy way to determine, if you've got the voltage measurements complex voltage measurements, say from your relays between two buses that are connected together, you can know right away, pretty much off the top of your head, hey, is there any real power flowing? If so, what bus is it being sent to? What's the sending bus? What's the receiving bus? Same thing. Is there any reactive power flowing? Is the reactive power net zero? Or is it a non-zero number? And what's the direction? Which way is it flowing? So that's even more helpful in the field. Make those quick ballpark, ballpark head calculations to help kind of guide your decision making, help guide your troubleshooting as well. All right, so we're going to start off with math. Again, if you're a recent PE and if you attended my class, you're probably real comfortable with this notation, complex numbers. If you're not, don't worry. We're going to cruise through this pretty quickly just to make sure we have enough time for Q&A. But all I'm going to do is I'm just going to walk you through these derivations so we can get to the final formulas. And then the final formulas are the ones that we're going to pick apart and see what happens as each variable changes. All right, here's the sending bus on the left. Here's the receiving bus on the right. We're going to calculate the complex power transferred from the sending bus on the left to the receiving bus on the right. What's the complex power received by this receiving bus? So over here on the left, here's just your standard complex power formula, right? S equals the product of V in the current conjugate. But notice the subscripts, right? Notice we have the complex sending power, which is not what we're solving for. And then we have the complex receiving power. We're calculating the complex receiving power. So we don't care about how much is being sent because some of that's going to be absorbed in this line. So we're only calculating how much power does the receiving bus actually receive minus any losses. This is where I've seen a lot of other textbooks, white papers, or videos go wrong. They solve for the complex sending power, but that includes all of your losses, right? We just want to know what makes it, what gets transferred, what gets received to the receiving bus. That's why we're using the receiving voltage and the receiving current specifically. All right, so the first step, all we're going to do is we're going to use Ohm's law for the current, right? We've got two voltages here, Vs and Vr. Ohm's law is I equals V over Z. In this case, our voltage is going to be the voltage drop across the conductor. I'm just going to call it Vx for the reactance. How do we get Vx? Well, Vx is the difference, subtract, between the sending voltage and the receiving voltage. That's it. Top of this fraction is the voltage drop across the reactance. Next, what's our complex impedance? All we have is a reactance. So we've got J of X on bottom. That's it. This entire I of R term is right here. That's the current flowing from the sending bus to the receiving bus. Next is we're going to use polar form for the sending voltage and the receiving voltage on the third line here. So polar form, we've got a magnitude and an angle. That's all we're doing. Complex Vs, now we've got our sending voltage magnitude and the sending voltage angle. No change to the minus sign. Instead of complex receiving voltage, we have the receiving voltage magnitude and the receiving voltage angle. That's all we've done on step 3. All right, step 4, it's time to apply the conjugate. How do we apply the conjugate to polar or rectangular numbers? All we do is what? If it's in polar, we change the polarity of the angle from positive to negative or negative to positive. Or if it's rectangular, we change the polarity of the imaginary component, right? If it's a plus j term, now it's a minus j term. If it was a minus j term, now it's a plus j term. That's it. So when we apply the conjugate, our sending voltage angle was positive. Now it's negative. No change to this minus sign. Over here, our receiving voltage angle was positive. Now it's negative. And then down here in the denominator, bottom of the fraction, our imaginary term, it was positive plus j of x. Now it's negative. That's it. That's all the conjugate is. We've successfully applied the conjugate. All right, now all we're going to do is we're going to take from step 4 to 5, we're taking our complex receiving voltage and we're going to distribute it into that bracketed term. So now I've got complex receiving voltage times complex Vs with the conjugate divided by negative j of x. Here's this minus sign, no change to that. And then again, we're distributing the complex receiving voltage into that bracketed term. So we've got our complex receiving voltage times, here's the conjugate of our receiving voltage, and here's the conjugate of our line impedance. All right, we're getting close. Promise this will be painless, but it will really help us understand the different relationships that these variables play with power transfer. All right, line number 5, this is exactly where we left off in the previous page. Now, all we're going to do is we're going to multiply the receiving complex voltage in polar form. Again, polar form has a magnitude and it has an angle. So here's the magnitude of VR times the conjugate of Vs. And then when we multiply two polar numbers, what happens to the angles? Who knows in the chat? If we multiply two polar complex numbers, what happens to the angles? Yeah, we add the angles. So before, here's negative Vs, theta, right? No change. All we're going to do is add the angle of VR to it. That's all. All right, no change to this negative sign. We're doing the same thing on the right-hand side term. We're multiplying by VR in polar. So now I have this magnitude times this magnitude, right? VR times VR magnitude. And then I'm taking the angle of VR and I'm adding it to this angle. I'm taking the angle of VR and I'm adding it to this angle. All right, now let's simplify a little bit. First of all, VR minus VR, what does that equal? Any number minus itself is always going to equal 0, right? So theta VR minus theta VR, this angle cancels out to 0. And we're going to be left with just a magnitude. That's 0 degrees. The next thing is we're going to simplify this angle right here. Delta, this is known as the torque angle. Delta is the difference in angle between the sending bus and the receiving bus. Delta is the angle of this voltage minus the angle of this voltage. Now, we don't quite have delta in here, but we have something pretty close. Look, if I move this out of the way, we've got negative parentheses theta Vs minus theta Vr. Does everybody see that? We've got whatever this is in parentheses times -1, right? We would have negative theta Vs plus theta Vr. Negative theta Vs plus theta Vr. So instead of our torque angle delta, we really have what? We really have negative delta. So this entire angle right here, we're going to simplify that to the conjugate of the torque angle, or just negative delta. All right, we're super close, I promise. The rest after this page is a lot easier. The next step is we're going to simplify the J operator. What does J by itself equal to? What is J? 90 degrees. Beautiful, Patrick. What's negative J? What does negative J equal if positive J is 90? Yeah, negative J is negative 90 degrees. So this is like a magnitude of 1 over 1 at negative 90 degrees. When we divide polar numbers, instead of multiplying their angles, like when we multiply, what do? Now we subtract their angles. So this is like an angle of 0 degrees minus an angle of negative 90. 1 minus a negative, that's the same thing as 1 plus. So 1 over negative J equals positive J. That means both of these negative J's right here, we're going to replace them with a positive J on top of the fraction. All right, last step. we're going to apply the J operator. We're going to go from rectangular to polar. J is equal to 90. What do we do when we multiply two complex numbers? We do what to their angles? We add their angles. So whatever my angle is here, I'm going to say plus 90 degrees. So I've got negative delta plus 90 degrees, or 90 degrees minus delta. And then over here, all I have is 90 degrees. So the square of the receiving voltage magnitude divided by the reactance at an angle of 90 degrees. And that's it. We just derived the complex receiving power all the way from just the standard complex power formula. Again, if you're taking the PE exam or recently taken the PE exam, you should be pretty comfortable with complex numbers and rectangular numbers and polar numbers. But if you're not, don't panic. You don't have to be able to do these steps to understand what we're going to talk about on the next slides. It just helps to tell you where they're coming from. And it'll help you recognize if you see other books, videos, white papers, resources in the future that are trying to calculate receiving power, but they're using the sending power variables and formulas, you'll know that, hey, that's not the same thing. That's two different things. We need to make sure we're accurate in what we call them. That's it for part one. Coming up next on part two, we're going to use that same formula for complex power that we just derived, and we're going to separate it into the real and imaginary components to derive the formulas for both real power and reactive power transfer. Coming up next.